Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to continue pretending like we're physics class and talking about energy. So specifically, we're going to focus on the different types of energy so we can be a little bit more clear as we proceed through this chapter and talk about how energy moves in and out of a system. Because fundamentally, thermodynamics is going to be about tracking the movement of energy, whether this is powering metabolism or causing a combustion engine to work. Now, when we're talking about energy, energy is defined as the capacity to do work. So this is also known as the ability to move an object against resistance. Because when we're talking about doing work, we're talking about making things move, doing something that doesn't want to be done. And that's really what energy allows us to do. Now, when we're starting with energy, we start by splitting it into two major categories: kinetic energy and potential energy. So when we're looking at kinetic energy, this is going to be the energy in a moving object versus potential energy, which is the energy stored in an object. So this is energy on the move versus energy that can move. So I always like using a visual for this. So if you wanted to think about kinetic energy, think about a waterfall. There's a lot of moving water, and that water, as it's falling, is exerting a ton of energy. It can definitely do work. It can definitely move objects that don't want to go anywhere, be it a rock or a boat going over the edge. In comparison, potential energy is going to be that same amount of energy, that same waterfall, but now it's stored so that it can slowly be released or released when you choose. So for this, I like thinking about a dam. We take that waterfall, we still have the water at the top is still able to exert that same amount of energy it does when it goes over the cliff, but now we release it slowly as it goes through a turbine and out the side. So both systems have the same amount of energy, whether it's stored or whether it's being exerted. And this is a very important concept because usually when we think about energy, we think about this great big movement. We think about somebody being energetic. We don't think about that candy bar in your back pocket giving you the energy for later. And both parts are going to be very important to pay attention to. Now, one of the big things is this idea of kinetic and potential energy can also be applied to chemical systems. In fact, we've already seen a fair bit of kinetic energy when we looked at our kinetic gas law. So this was the idea that atoms moving around can exert a great deal of energy. And by tracking that amount of energy, we can make a lot of different predictions. However, this kinetic energy can be in several different forms. So when we were talking about the kinetic gas law, we mostly were looking at the kinetic energy of a single gas molecule moving along a straight line. So this came from this idea that the kinetic energy, so that energy in that translational movement, was going to be 1/2 the mass of the molecule moving times the square of its velocity. And this is just going to be straight kinetic energy, which can hit the wall and exert a great deal of pressure. However, kinetic energy can often also be associated with other types of random motion. So sometimes our translational motion can be random. We don't know which direction our gas molecules are going to go in. However, it turned out with our kinetic gas law, we were ignoring other types of motion. It turns out those molecules can also rotate and they can also vibrate. And these types of random motion will also be able to store random kinetic energy. So this type of random kinetic energy is called thermal energy. It's not energy being used to move an object, it's going every which way. And this thermal energy is what we're monitoring when we're looking at the temperature of a system. However, these chemical systems can also store potential energy. And this potential energy is usually located either in electrons being someplace they don't want to be, or another form of electrons being someplace they don't want to be, unstable chemical bonds. So a bond that, exists, but it's not the happiest bond it could be. And if you move from a high energy state to a low energy state, this is going to release some energy from the system. And in fact, we've seen this before, whether it is an electron sitting in an excited state, so sitting at, say, the n=2 level. When it goes down to the n=1, it releases energy, and it releases that energy as a photon. But this is also important, say, in biology. When I go from ATP to I release a phosphate and I go to ADP, you release a great deal of energy, which can be used to drive metabolic processes. Both of these are forms of stored potential energy. One in terms of an unstable electron being someplace it doesn't want to be. And in the second, phosphates don't like making 3 phosphates in a row. That triphosphate, very unstable, and that unstable nature is exactly how biology stores its energy. It's like a mill pond. You can store energy in a place it doesn't want to be and slowly release it to do work you want to. In this case, to drive other chemical reactions. In the case of the mill pond, to drive that wheel. However, this chapter, we're going to focus on 2 simpler forms of energy, and specifically 2 simpler forms of energy movement. These are going to be heat and work. So heat's going to be the transfer of thermal energy. So this random motion from one region to another. And it turns out heat always goes from the higher temperature region, so the region that has more kinetic energy, to the lower temperature region, the one that has lower kinetic energy. And you can think about this as I'm going to have, say, a high energy atom hits a wall, bounces off, and it's transferred some of that energy in a collision to the wall, which then can exert that same amount of energy to another molecule on the cold side. So I'm moving that kinetic energy from one atom to another. And because of the random nature, we always tend to go from high energy to low energy as it spreads itself out. And this is the major idea of heat transfers. However, so far we've been looking at this thermal energy of random movement of energy. There's also a much more directed form of movement of energy, and this is going to be work. So work is going to be the application of force required to move an object a specific distance. So think about this, the amount of force it would take to move a boulder 10 feet. That will give you the work done. However, we can use a physics definition of force being mass times acceleration, and we can separate it out into the work is going to be the mass of the object I'm moving, how much acceleration I put on it, and the distance it moves. However, you can apply this, as you might expect, to pistons. And in a piston, the work done by a piston can be related by the mass of the object, the acceleration is provided by gravity, and the change in height of the piston is going to give the work done. However, since there will be a sign inversion, because if I move the object will be a sign inversion. As I move the object up, we have a negative work. So that said, there are many other types of work that can be done, many other types of energy besides heat and work. And some of these we've encountered and some we haven't yet encountered. So one of the big ones is electrical energy, which we're going to be talking about next semester. With redox chemistry. And so this is going to be the kinetic energy associated with the flow of electrons. So I'm going to give some energy to an electron, and it will carry that energy with a certain amount of kinetic energy with a certain velocity. And that's going to give us the electrical force, so voltage. We have, however, encountered light energy. So this is also called radiant energy. This is the energy in a photon. So as we've seen, photons tend to carry their momentum in their frequency instead of their speed. So a photon with a higher frequency has more kinetic energy, and it can thus do more work. And this generally is produced by those energy transitions in an electron or an atom as we move in between different orbital levels. The last one, which we're going to also talk about next semester in more detail, is nuclear energy. So it turns out that nucleons, so protons and neutrons, tend not to like to be too near each other. So they have optimal placements and bad placements, just like bombs. And as a result, this is a way to store potential energy, which can be exerted as kinetic energy when you have a nuclear reaction, which often releases some photons and some high energy particles, including electrons. So nuclear energy will kind of be where we end off next semester as we bring a lot of different things together. So next time, we're going to be taking these these types of energy and develop a certain set of rules of how we can look at the energy of a system and make use of the first law of thermodynamics. Until then, take care.